Hello everyone, welcome to our YouTube channel Electronics Maddie. In this video, I am going to demonstrate closed loop simulation of three-phase control rectifier in PSIM. In case you haven't subscribed to our channel, please do subscribe to it so that you'll be getting the videos that we post regularly. Alright, let's get into our topic for today. This is a PSIM model of three-phase fully controlled rectifier operating in closed loop mode. So at the first place, let us try to understand what this circuit is all about and what are the things that we're trying to achieve with this circuit, and then we'll start off with the simulation in PSIM. So we're basically using three-phase source given to a three-phase thyristor bridge. Consequently, you'll be getting DC output. Using inductor and capacitor will reduce the ripple content that is there, and we are giving it to a resistive load. The voltage that is obtained, we are obtaining that using a voltage sensor, determining that, and we are giving it with a summation block in comparison with a DC signal. So the output is also DC here. We are giving a DC voltage, the reference value, whatever output you want. I'll repeat again, whatever output you want at this point. If you want 100 volt at the output, set that over here. So that voltage will be compared with the output voltage that is there. Consequently, the difference will be given to a PI controller. PI controller will reduce the steady state response or the transient response that you want to, and ideally it will be given to a saturator, that is basically a limiter. So you're giving it to a cos inverse block, so that means the signal range should not be greater than 1, it should be between 0 to 1, isn't it? So as a result, what we will be doing is we will be limiting this between -1 to +1. So if the value at this point is 2, then the maximum value will be 1, that is limited. So it will take 1 as the maximum value, and it will take the cos inverse of that value, and it will be given to an alpha controller. This is basically used to give the gating pulses to the thyristor bridge, but it also has several different inputs, isn't it? So what are these inputs? I'll be comparing the reference voltage at this point, that is with respect to the supply voltage. I'll be taking that value with using a voltage sensor. I'll be giving you to a comparator. This basically converts the signal into a square wave, that is between 0 to 1. Maximum values between 0 to 1 you'll be getting at this point. So why is that used? So this is called as the synchronization terminal of the alpha controller. So when it is between 0 to 1, when the signal goes from 0 to 1, alpha controller will be activated, and the value that is obtained at this point will be taken. And what is this block? Step signal. This is used as enable. This terminal is called as enable for alpha controller. In order to enable this alpha controller, you will be using a step signal. So this is how it is actually programmed in PSIM, and that is why we have to follow this logic. In MATLAB, we have a different procedure altogether. I've already made a lot of videos on that as well. So this is how we have to understand and analyze the operation, and based on the deviation in the output. So if there is sudden change in the supply voltage or sudden change in the load, and consequently you should still be getting the same amount of voltage without any fluctuation. That is what we are trying to achieve. So let us go to PSIM and start our simulation over there. Alright, here we are in PSIM. We have this menu where we can directly take the components, drag and drop them over here. In case you don't have the components that are required for your circuit, you have to go to the respective blocks. So I'll start off with this. So go to elements, go to sources. I'll be requiring a voltage source, three-phase sine wave. So add this block, and we need a ground for this. So let us complete part by part with respect to the circuit. I'll be connecting ground at this point. Once this is done, again go to elements, go to power section, and go to switches, and I'll be requiring a three-phase thyristor bridge. So choose this, and I'll be giving it to these blocks respectively, constructing the input side of the rectifier circuit. So once this is done, now I'll be using an inductor. I'll be connecting it over here, and I'll be using a capacitor. I'll be connecting it over here, and I'll be using a resistor. So I'll be connecting it over here. So once this is done, I'll be connecting this in series with the thyristor bridge and a capacitor across it, and I'll be giving a resistor at this point. So resistor is the load that we are using it. Double click on the inductor, and I'll be giving an inductance value of 10 millihenry. You can design according to your requirement. I want to reduce the ripple as far as possible, so I'll be entering 100 micro. Let the resistance be value as 10. Once that is done, we will be requiring a voltage sensor. So over here, if you carefully, when you place that on the component, it gives you an indication as what type of component that is over here. So I'm placing it, you can see voltage sensor. So add this block. This will sense the amount of output voltage. So I'll be connecting it between these 2 points, this particular fashion. So I'll delete this. I'll connect, let me connect this properly. So if you see, there was an additional node that is found. So that is one of the major concerns in this. So be very careful while connecting them. I'll be placing this a little in this particular fashion. Now I'll be connecting it at this point to measure the voltage. Once this is done, I'll be requiring a DC voltage source. So over here, and I'll be requiring a ground for the DC voltage source. And this needs to be compared. So I'll be using a summer block over here, connect it over here in this particular fashion, and I'll be comparing it with the output voltage that is obtained in this particular fashion. So once the voltage is compared, I'll be requiring a PI controller, that is here. Give it to the PI controller. I'm not entered the values of a few of the parameters. I'll enter it later, and I'll be giving it to a limiter. So with respect to limiter, it is directly available over here. So if you carefully observe, there will be a block called as limiter over here. So add this block as well, and I'll be connecting it. So this will basically limit the values. And apart from that, we require a cos inverse block, isn't it? So go to elements, go to control, and go to computational blocks, and we'll be requiring an arc cosine block, that is basically cos inverse, that is labeled as cos inverse in PSIM. So connect it in this particular fashion. So once that is done, we'll be requiring an alpha controller. So go to elements, go to uh, other block in this, and then go to switch controllers, and then go to alpha controller. So this is used to generate the pulses for the thyristor bridge. So the switching pattern based on the changes in the load or changes in the supply. So once that is done, we will also be requiring a comparator. So comparator is available over here at this block. And apart from that, we will also be requiring a step signal. So we will be having step signal over here as well. If you carefully observe, this is the step voltage source. So add this as well. For the step signal, we will be requiring a ground. So connect it to ground in this particular fashion. And for the comparator also, we'll be requiring ground. Connect it in this particular fashion for the negative terminal. Now again, voltage should be measured. So rotate this, and over here, I'll be connecting it between the phase voltage, that is between phase A and phase C. So in this particular fashion, once that is done, I'll be giving this from this point to the comparator, and the comparator will be generating a square wave, and that will be given to the synchronization block of the alpha controller. And this is to enable the signal. So when you're giving step input, and if you double click on it, V step is 1. So when it is 1, alpha controller will be enabled. Otherwise, even though you generate the pulses, alpha controller will not work at this point, and you will not be getting any output with respect to the circuit that you have simulated. So be very careful. So over here, we have to connect this between these 2 points. If you see, there is a node that is generated, so we don't want that. So we will delete that section. We will delete this as well. We'll delete this point. So we have to be very careful with respect to the nodes. So I'll be placing a ground block over here, and I'll be connecting it at this point in this particular fashion. So once this is done, we will be entering the values. Let us say the line voltage is 230 volt. I'm not going with an accurate design. Let us say the the frequency is equal to 50 hertz, and we will be having a frequency of 50 hertz at this point as well. Set the pulse width that you want based on the value of alpha that you want to initially trigger the circuit for, and these values are already entered. Double click on this. Let this be equal to 100 itself. Double click on this. Let us change the value of the gain to be equal to 0.01. This is something that you have to design. So there are various design techniques available. You can refer to that. You can do it based on Laplace transform, like the transfer function approach. You can use that in order to design it. Let us set the lower limit and upper limit to be equal to -1 and 2 plus 1, because cos inverse of that range only the signal will be available, isn't it? So that is why we'll be doing that. So apart from that, we will be requiring a voltage measurement block at the output terminals in order to measure the voltage. I'll be connecting it between these 2 points, and We will also be requiring a voltage sensor just to compare. Let us first check the output, and then I'll be making a lot of changes with respect to the reference values, and I'll test the circuit in various different conditions. So we have rigged up the circuit. This is how we have to construct the circuit. Now we will be requiring a simulation control. This is important for the simulation to take place. In order to have control over the simulation process, you need to have it. Otherwise, you'll not define any time, and automatically you'll not get the entire x-axis scale. So the scale of x-axis can be decided over here. So now let us click on run simulation. So it will be asking for the input that you want to see. If there is only one output, directly it will display that value, as it in this case. So if you carefully observe, you are getting a DC voltage, and the mean value is say equal to 100 volt. So there, however, there is some amount of ripple if you carefully observe over here. This can be further reduced by designing suitable value of capacitance. By having a large value of capacitance, you can reduce the ripple. But if you see, the mean value is 100 at this point. So this is exactly what we wanted. Now let us check the circuit. Now how do we justify that this is a closed loop mode? Now let us change the supply voltage directly to 300, and let us see if the circuit is still producing 100 volt. And if it is producing 100 volt, then the circuit is exactly what is to be operating at. And if you observe, we are still getting 100 volt. So that means we are still getting 100 volt even if there is changes in the supply. So there are chances that the supply that is used, if you're using a generator, so there are chances that it might not consistently produce the same amount of voltage. It might drop down at some point of time. In that case also, we still have to get the same amount of output voltage, otherwise the loads that are connected might be damaged, and that is why closed loop systems are popularly used. So I hope this concept is clear. Now let us try by changing the amplitude over here. Now if we set 150, I have to get output voltage of 150. This is the reference value. Whatever output voltage that you want, you have to set it over here. So now let us click on run simulation again, and we can zoom in the specific range of the output waveform in this particular fashion. So you are exactly getting 150, the mean value over here, and that is what is decided. So what is happening at this point? Let me show you step by step. So you are getting a signal. So this is basically a sine wave, isn't it? At this point, you'll be having a sine wave. At this point, you will be getting a square wave. And let us compare it with the pulses that is produced over here. So now let us click on run simulation, and now it will be asking for what all the values that you want to see it for. So let me say V1 and V2 is what I want to see. Now let me split these waveforms. Let me use V1 separately, and let me again split this to see V2 separately. So click on add. So what we will be doing is, now I'll be zooming a specific region. Let us zoom in this particular region. And if you observe, V1 is nothing but the output of the comparator block. When the signal goes from 0 to 1, that is where I said the alpha controller will start enabling its circuit. And consequently, at this point, if you see, the pulses starts generating. And if you see, the pattern of the pulses keeps changing, isn't it? So you will not be getting a uniform pulse pattern, and that is where closed loop plays a very important role. If you have a constant pulse generator block, then the output voltage will remain constant based on the pulses that is produced. So if you see, these are variable pulses, and this is how closed loop mode can be achieved. I hope you were able to simulate this circuit on your own. If you have any questions, feel free to reach out by typing in your questions in the comment section below. If you like this video, please to like it, share it, and subscribe to our channel for regular updates. Thanks for watching this video. Please to keep supporting. Thank you.